Hello and welcome to the SignFlex showcase for Group 28. The SignFlex team consists of 2 computer engineers and 2 electrical engineers, Antonius, Ryan, Madison, and Esteban. The objective of the SignFlex project is a technical solution for the disconnect between those who speak American Sign Language and those who do not. Our team is looking to bridge the communication gap between the 2 groups utilizing modern technology. Our solution is a wearable glove that accurately recognizes and translates the American Sign Language alphabet and provides the user real-time translation and feedback using a mobile application. For our system overview, we have 3 main portions of our glove. In the wristband, we have our PCB storage. Our PCB houses our accelerometer, our battery monitoring system, and our regulators, as well as the connections for the flex sensors. In the opposing pouch, the batteries are stored on the opposite side, consisting of 2 lithium-ion batteries. The PCB then has JST connectors that wrap around the wristband with the wires, as you can see in the photos, and connects to the 5 flex sensors, 1 for each finger. And now we will take a look at our custom PCBs. For the SignFlex team's PCBs, the team ordered 2 regulators and 1 main PCB. For our main PCB, it consists of 4 layers and has the following: micro GST connectors for flex sensors, a USB-A connection for uploading data to the ESP32, an ESP32, our fuel gauge and battery monitoring system, as well as our accelerometer for measuring tilt and hand orientation. And pictured on the right-hand side of the screen is our 3.3 volt regulator for our accelerometer, fuel gauge system, and ESP32, as well as our 5 volt regulator for our flex sensors. And now we will demonstrate our 3.3 volt regulator. As you can see on the breadboard, we've connected our custom-made 3.3 volt regulator to a power supply and an electronic load. On the power supply, we're giving our 3.3 regulator 5 volts because this would be the output of our 5 volt regulator. And going to the electronic load, you can see that at that voltage, it's giving us 3.3 volts, which means that our 3.3 volt regulator is completely functional. And now we will be demonstrating our 5 volt regulator. As you can see on this breadboard, we've hooked up our 5 volt regulator to a power supply and an electronic load. Now, going to the power supply, you can see that we're giving it 7.4 volts and 3 amps. This is because the 7.4 volts is roughly about what our batteries are giving our PCB, which is what would be translated into the 5 volts with the regulator. And as you can see on our electronic load, we are given an output of 5 volts, which is demonstrating that our 5 volt regulator is completely functional.
This is the main PCB, which holds the majority of the significant components in the overall system. The ESP32 chip located on the top left corner of the PCB will serve as our MCU, which will be receiving and transferring data from the accelerometer, fuel gauge system, and the 5 flex sensors over to our mobile application. The USB to serial bridge CP2102 is located as U6 between the microcontroller and the USB-A connector, which will allow for serial communication. The LSM6DS3TR-C accelerometer, located as U8, will measure the movement and orientation of the PCB as it moves in the X, Y, and Z axis. The BQ24771-G1 fuel gauge system, located as U9, will measure the voltage of a single battery cell inside the battery holder, which will also be reflected on the mobile application. And the 5 JST connectors that are located on the far right of the PCB will serve as the connections that allow for the flex sensors attached on the glove to be connected to the PCB.
So now I'm going to walk you through the computer vision aspect of our project. This was a key part of our system that allowed us to classify American Sign Language letters using hand gestures in real time. So we started by training our ASL classifier using a custom dataset of hand gesture images. The graphs here show the training and validation performance were over 25 epochs. As you can see, the model quickly reached almost 100% training accuracy, and the validation accuracy settled around 92%, which is showing that our model learned the gesture well and generalized it very good. The loss curves confirmed that with our loss training dropping sharply and validation loss showing a bit of variability, which is typical for our ASL model. Overall, The results were strong and indicates that our model was ready for real-time use. And once the model was trained, we deployed it in our Android app and we tested it with our SignFlex glove. And as you can see in these pictures, the results of the letter A and the letter B, the system consistently predicted them correctly, with response times around 20 to 27 milliseconds and accuracy between 91% and 99%, which matches our requirements for this project. This showed that our model wasn't just good in training, but also performed very well and reliably when used in live with our glove.
In this scenario, we'll be demonstrating the computer vision.
A, B, C, D, F, D, F, L, Y, Q, N, M, W, X, R, V, L, V, T.
Now we're going to show the mobile app. This is our dual mode ASL recognition system, also known as our mobile app interface. We have 4 screenshots showing certain features of the app. If you go to the left side, our first screenshot is our login and authentication. You can see that we have you can log in with the username and password, but the picture I have showing is the registration feature where you can obviously register for an account. And if you go to screen 2, you can see the profile button, and you can go back to change your username and password and other features you like to change. If you go to screen 2, you can see it's our intuitive navigation with our clear action buttons, showing all the other features of the app, where you can do the direct connection to the ESP32 and all other features featuring Bluetooth. Also with our camera ASL, glove sensor, and dual mode, and it gives back real-time letter prediction display with visual feedback. If you go to our right side, with the screenshot number 3, you can show our dual ASL recognition, which takes the Tony computer vision and our flex sensor output and fuses the data to give one correct output. We have it where thresholds of 80+% accuracy, so it doesn't constantly spit out random data, so we can make sure it's always giving something accurate and reliable data. And it gives you feedback such as waiting for accurate signal for low confidence detections. If you go to screen 4, we go back to the main screen, and you can see the comprehensive glove sensor reading display featuring the battery monitor and the flex sensor ankle measurements for all 5 fingers that it's getting from the ESP32. Also with real-time metrics tracking. Yeah, so overall, the SignFlex mobile app provides comprehensive ASL recognition solution with camera-based and heart rate-based.
For this portion, we will have a project demonstration highlighting our engineering specifications.
And now we'll be demonstrating our moving letter, which is J and Z. So we start with J.
J,
Following up our second movement letter, which is Z.
Z,
In this scenario, we'll be demonstrating static letters.
A, B, C, E, G, P.
Thank you for watching our video.